Section 1.2 Row Reduction and Echelon Row Forms. Recall that in section 1.1 we learned a technique to kind of we followed a technique where we try to make the matrix, augmented matrix, into an upper triangular matrix in order to find our solution. Then we used back substitution. So this method that converts the triangle, the rectangular matrix into a triangular matrix, upper triangular matrix, and then using the back substitution, finding the solution, is called the Gaussian elimination. In this section, we will learn an efficient way to find the solution of linear equations, and this is actually going further than the already reduced triangular matrix, making some more changes in that. And now we have some proper names. Instead of upper triangular matrix, it's the matrix form is called echelon form. So we say a rectangular matrix is an echelon form or row echelon form. So both words are used, echelon or row echelon, if it has the following three properties. So first is all non-zero rows are above any rows of all zeros, or you can say all rows consisting of zeros are grouped together at the bottom of the matrix. So if there is a row which has all zeros in it, then it must be below or at the bottom of the matrix. Second, each leading entry of a row is in a column to the right of the leading entry in the row above it. Okay, let me show you an example here, and this will make you see. So let's look at this matrix B down here. So first line, all non-zero rows are above any rows of all zeros. So actually we will look at both A and B. So if you notice, the first entry is saying first statement is saying all non-zero rows are above any rows of all zeros. So if you notice in matrix A, there is no row of zeros. So we don't have to worry about the first statement or first condition. But in the second, in the B matrix, there is a row of zeros and it is at the bottom of the matrix. So that condition is satisfied. Second is saying each leading entry. Now, what is a leading entry? Remember, it is the first non-zero entry in a row when we go from left to right. So the second condition is saying each leading entry of a row is in a column to the right of the leading entry in the row above it. So in other words, going from left to right, the first non-zero entry in the I plus 1 row. So there could be a lot of rows. We are looking at a matrix of 4 rows and a matrix of 3 rows, but we could have 50 rows or 100 rows. So we're going to generalize the statement. So if you say this is the I plus 1 and this is the I. So then the leading entry in the I plus 1 is here and leading entry in the ith row is over here. So this is saying going from left to right, the first non-zero entry in the I plus 1 row, which means the 2 here, must appear in a column to the right of the first non-zero entry in the ith row. So you can see it is to the right, in the column to the right. Same thing over here. So the first non-zero entry in the first row is 1. The first non-zero entry in the second row is 3, and it is to the left of the it is in the column which is to the right of the first column. third condition is that all entries in a column below a leading entry are 0. So if you notice, this is the leading entry here, and all entries in that column below the leading entry is 0 are 0. This is the leading entry in the third row and second row, and it has zeros below it. Then third row has the leading entry 2, and we have zeros below it. Same thing over here. Now this last one, remember, is the column is not a coefficient matrix. This is part of the augmented matrix. So it is something we are getting from the, not the coefficients, but the numbers which are to the right of the equal to sign. So these two are in echelon form, A and B. Okay, so the next thing is, if a matrix in echelon form satisfies the following additional conditions, then it is we can say it is in reduced echelon or row reduced echelon. So these are kind of referred to as RREF, and this or REF, and the other one was just EF or REF. So this is some function key in many calculators through which you can get the matrix in that form. But if you know how to do that on a calculator, you can do it only to check your answer. You are not supposed to use the calculator just to find the row reduced echelon form. You have to show all the work. Okay, so then if these two conditions are included, then the matrix becomes in, we can say it is in row reduced echelon form. So what are those conditions? That the leading entry in each row is 1. Now notice here in this matrix A and B both, we didn't have all leading entries equal to 1. We have a leading entry in A here, which is 3. We have a leading entry of 2, and we have a leading entry of 4. In the same way over here, leading entry 1 and the leading entry 3. So these are not in reduced echelon form, but if they are 1, and we can easily make them 1 by multiplying, for example, the third row here by 1/2 and the fourth row by 1/4. And similarly, same thing we can do in this one. So that is something extra we have to do. And then the last condition is that each leading one is the only non-zero entry in its columns. So now previously we said all the entries below a leading one or below the first non-zero entry must be 0. So now, and we didn't say put any condition on the entries above the leading entry, but now the leading entry must be 1, and all the rest of the entries in the column should be 0. So let us look at these two, C and D. They satisfy the condition of reduced echelon form or row reduced echelon form. Why? Because notice here now, so we have, this is the diagonal, and you can see each diagonal entry is 1, so each leading entry is 1, and then we have zeros everywhere above and below the leading entry. So that's why this is in reduced echelon form. So if you look at the D matrix, now here a little bit diagonal doesn't actually kind of work completely, but this is the diagonal here. So that condition is satisfied, which we had before, that below it the there are zeros, entries are zeros, but what about above it? So in this case, our definition or our speculation with the diagonal won't work. There is another way people look at this condition of zeros is thinking of the staircase in the matrix, making a staircase like this. So if you get this type of pattern, then it is in echelon form. And if you have zeros above the diagonal, then as well, then it is in reduced echelon form. So we could use the same thing over in here, the staircase. Okay. And looking at the staircase here, so notice here that the height of the stairs is same, but the length or the width of the stair could be different in places. So why are these two C and D in echelon form, reduced echelon form? Well, because first one is easier because we have all ones on the diagonal and then all zeros below those ones and above those ones. So this is in row reduced echelon form. How about the second one? The second example here, D. So making a staircase. This is how we went, okay? So this is the first non-zero entry. This is the first non-zero entry. Now in the second row, the first non-zero entry is in the third column, and the third column is to the right of the first column. So that condition is satisfied. Now in the third row, we don't have any non-zero entry, so we are okay. The other condition was that so going to the echelon, because the reduced echelon form must satisfy all 5 conditions. So the first condition is that if there is a row of zeros, it's at the bottom of the matrix, which is what we have here. And the second was that each leading entry should in the next row should be to the right of the leading entry in the previous row. So that is what we see in there. Third condition was that all entries below the leading entry must be 0. So that's what we are seeing. This is the leading entry in the first row, and this is the leading entry in the second row. Now we do not have a leading entry in the second column. This is the leading entry of the second row is in the third column, which is okay, which can happen. So we have zeros below and above the leading entries. You can see that we have zeros above and below the leading entry, and then the leading entry is 1. So yes, this is also in echelon form. The next two are not in echelon form, so reduced echelon form. And why? Okay, so the first condition is that if there is a row of zeros, should be at the bottom. When I look at both M and N, there is no row of zeros, so first condition is devoid. The second condition was that the leading entry in the I plus 1 row should be to the right of the leading entry of the ith row, previous row. So here the leading entry is 1 and then the leading entry here is 1. So we are good. And in here the leading entry will be this one. So the diagonal, below the diagonal, do we have all zeros now? No, we don't. So this is not in echelon form, and not in reduced echelon form. So remember, a matrix may be in echelon form and it may not be in reduced echelon. But if it is in reduced echelon form, it means it is in echelon form. Now here, this is the diagonal, and leading entries satisfy the condition that the leading entry in the second row, which is over here, is to the right of the leading entry in the first row. And or in this case, all the entries in the below the diagonal are 0. The diagonal is like this. So all the entries below the diagonal are 0, but not all the entries. So this this one is an echelon form. Okay. So they are not in reduced echelon form, but they could be in echelon form. So this one is echelon. This is not echelon. So if not echelon, it is not reduced echelon. Not reduced echelon. Not echelon. It is not reduced and it is also not an echelon. So this one is not reduced echelon, but it is echelon. So it is echelon, but not in reduced echelon. Okay, so there is a theorem saying the uniqueness of the reduced echelon form. So each matrix is a row equivalent to one and only one reduced echelon form. Okay, so no matter how you approach it, with what steps or transformations you make in the matrix, if you are trying to convert it into reduced echelon form, there is only one way to look at it, or it always reaches the same matrix. So now we have some proper names for things. So the leading entries that we were using in these matrices, the leading entries of the rows, those are actually called pivots or pivot positions. So a pivot position in a matrix A is a location in the matrix A that corresponds to a leading one in the reduced echelon form. A pivot column is a column that contains a pivot position. Or sometimes we just say pivot. A pivot column is a column that contains a pivot or pivot position. So what is the algorithm, the efficient way of finding the reduced echelon form? So this is the procedure. Basically, remember, we have explained it before. So step 1 is begin with the leftmost non-zero column. Now remember, it will be always the first column is the one which has the non-zero entry in the first position. So which means the leading entry of the first row must be a non-zero value. This is the pivot column. So the first column is always going to be a pivot column, and the pivot position will be at the top. Second step you do is select a non-zero entry in the pivot column as a pivot. if necessary, interchange rows to move this entry into the pivot position. So if your first row, in the first row, the first position has 0 in it, then we have to interchange with that first row with some other row, so that we get a non-zero entry in the first position. So if necessary, interchange rows to move this entry into the pivot position. Step 3 is use row replacement operations or to create zeros in all positions below the pivot. So the first process is going to be, I'll show you. Okay, let's make it. So if my augmented matrix looks like this, so I have in the first column I have a 0 in the first position, so this cannot be the pivot, but this is a pivot position. The pivot position is this one, so we must have a non-zero entry in there. So how do we get that? We swap or we interchange the first row with the second row. So then we will make the sometimes it's easier to do it this way, that we convert or we apply a row operation to have a 1 in the pivot position, because if we are going to use the row reduced echelon form, so we have to have the pivot as 1. So we will multiply the first row by 1/2, and then we will use that to make zeros below the pivot in the whole column, first column. So if there were more rows, we want in the first column we want 1 in the first place, and then all the other places are zeros. So it's step number 3 is saying use row replacement operations to create zeros in all positions below the pivot. Second, next step 4, it says now cover the row containing the pivot position and cover all rows above it, and then apply the procedure 1 through 3 to the smaller matrix or the sub matrix that remains, and then we keep repeating until no more non-zero rows are left. This procedure up to step 3, actually in this case up to 4, we can now use back substitution, but if we wish to reduce it further to get it reduced echelon form, we have to do one more step, and that is to make all the entries above the pivots 0. So that's how we do this. Now let me show you some examples here by looking at these matrices. These are all augmented matrices, assuming it says here determine whether the matrices are in echelon form or reduced echelon form or neither. So if you want, as I mentioned in section 1.1, you can draw a vertical line here, because that separates the column of b values to the right, and these are our coefficients, our variables. So in this case, two variables, two variables, two variables. This has 3 variables, and this one has 4 variables. Okay, So it says determine whether the matrices are in echelon form or reduced echelon form. So what do you think of the first one? Well, you can use the diagonal technique here. So you see the diagonal. Below the diagonal, everything below the diagonal is 0, and everything above the diagonal is as well as 0 also. So it could be the reduced echelon form. What is another one more thing we have to check to make sure it is reduced, that each entry in the on the diagonal is 1, which it is. So this one is in reduced echelon form, or we can say RREF. Next one, so this is your diagonal. So all entries below the diagonal are 0. Entries above the diagonal are not 0, or this is fine. Entry on the diagonal, not all of them are 1. So this is echelon form, or EF. Kind of same thing here. So we have a row of zeros and it's at the bottom. The rest is similar to the second matrix here. So this is also in echelon form. Looking at this fourth matrix, the 3 by 4. So this is the diagonal. So you can see all entries below the diagonal are 0. Entries above the diagonal may be 0 or not 0, but and also the entries on the diagonal are not all 1. This is in echelon form. Last one here. So it has 4 variables. It's an of order 3 by 5 because there are 3 rows and 5 columns. This is our diagonal. So we could have said it's in echelon form. Of course, it's not in reduced echelon form. But why is not in echelon form? Not EF, not, let me call it row echelon form, or not REF, row reduced echelon form. Why? Because the entries below the diagonal is not 0. Also, if you notice here, another condition is being failed because the entry in the third row is to the left of the entry in the non zero entry or leading entry in the third row is to the left of the leading entry in the second row. So that condition also fails. So that's why it is not even in echelon form. Okay. Now next is we have to be able to write down our solutions. So write the solution of the linear system corresponding to the reduced augmented matrix. So these are augmented matrices which are given in reduced form. So reduced echelon form. So we have just to write the solutions. What we do, we remember that these are the coefficients of the matrix, and then we have to write down the equations now. So the first equation here will be x1 minus 1/3 x3 is equal to 4. Second will be x2 plus 3x3 equals 4/3. And the last row will give me 0 equals 0, which is a true statement. So from the first equation, I can write x is equal to 1/3x3 plus 4. And second one, I can write x2 equals negative 3x3 plus 4 over 3. So this means x3 is free variable, and we say let x3 equals t. Then we can write our solution as x1 equals 1 over 3t plus 4, and x2 equals negative 3t plus 4 over 3. And if you want to write it in the this will be comma plus 4 comma, oh, by the way, there was an x3 here, so x3 is t. There are 3 variables, so we should give the value of each. So this is how you can write your solution. So this, you can see, it has infinitely many solutions. Okay, looking at the next example. So again, we have a matrix of size 3 by 4. There are 3 variables. I write my equations. First equation is x1 plus 5x2 plus 5x3 equals -1, and that's it. I don't have a second or a third equation. I mean, they both give me 0 equals to 0. So what does that mean? It means x2 and x3 are free variable. How do you figure out which are the free variables? Well, basically, you can see that if we consider this as a pivot, then there is no pivot in the second or the third row. So that's why those are your free variables. So I can say x1 equals negative 5x2 minus 5x3 minus 1. Again, now, because these are free variables and they should have a separate symbol to represent them. So let's x2 equal to t and x3 equal to s. Then our x1 will be equal to negative 5t minus 5s minus 1. x2 will be equal to t and x3 will be equal to s. So our solution will be minus 5s t minus 5s minus 1 comma t comma s. So now look here, 5 and s kind of look similar, so just be careful to write properly so that it is distinguishable. Part C, we have x1, x2, x3 and so on. So from the first equation I have x1 equals 1. From the second equation I have x2 equals 2. And from the third equation I have 0 is equal to 0. So what does that mean? Well, there have to be 3 variables, so we should be able to see what we are not getting a specific value for x3, but we are getting a true statement, so we say that x3 is a free variable. So we say let x3 equal to t. So your solution will be all numbers of the type 1, 2 and t. Okay, last example. So again here x1, x2, x3, x4, x5. So we have 5 variables. this is the b. So write the equation: x1 minus 2x4 plus 2x5 equals to 0. x2 minus x4 plus x5 equal -1, and the third one is giving me x3 plus 2x4 plus 3x5 is equal to 2. So notice here in the matrix that the pivot positions are only in the first, second, and third column. You can circle them. There are no pivot positions in column 4 and 5. It means for the variable x4 and x5, so they are free variables. So let x4 equal to t and x5 is equal to s. Then x1 is equal to, because it will become 2x4 minus 2x5, which means 2t minus 2s. x2 will be x4 minus x5 minus 1, which means t minus s minus 1, and then x3 will be what we have here. So negative 2x4 minus 3x5 plus 2, or negative 2t minus 2s plus 2. So what will be x4 t and x5s, and in the tuple form you should be able to write these values. This is how we write down our solutions.